So first, let's talk about linear classifiers, and not actually how we're going to learn how to classify, but the framework for making a decision based on your weights. So the setup here is that you're going to have x, which is the object that you're trying to classify. So x is, for example, it could be an email, and you want to determine whether it's spam or ham. And then what you do is you build up a feature vector, f of x, that is based on your example here. And what you'll do is you'll have some code that will count, for example, if one of your features is your name, whether it's not in the email, then the value of that feature will be 0 for this instance. And then if another feature is the number of misspelled words, then you'll have some code that will compute this feature based on the example that it gets. And then a third feature could be whether it's from a friend or not. And once again, you'll have some code that will take each of your examples and turn it into this feature representation. Then what you do from this feature vector is you determine whether or not it's spam or not, and whether you classify whether it's a positive label or a negative label. And so that's what we're going to talk about today. We're not going to talk about how you build up these features and how you create these features, but rather how you go from this feature vector right here to your label. And your label, in the case of binary classification, will be +1 for spam or -1 for ham. And another example might be if you have a number where this object could be like a PNG of an image, and you want to determine what number is in that PNG, then you'll have some code that will build up a feature representation of that image, and that'll make up your feature vector. And then from that feature vector, you'll make a classification. And in this case, the dimensionality of your classification will be 10. You'll have 1 for each number. And the goal is to make an algorithm that can efficiently go from this feature representation to determining the classification, which is the number. So some of the inspiration for the Perceptron algorithm was actually from humans. It's very loose inspiration, and that you can go pretty far saying that you built it. I mean, it's a very simplified model, essentially. So you might see if you have a human neuron, then you have some electrical signals that are going into the dendrites of the neuron. And then this neuron has a job to do, and it has to determine, say for example, it has to determine whether it sees a face. And then what it does is it takes all of the electrical signals, and if it gets enough signals from cells, incoming cells, then it will, and if that sum increases, goes above some threshold, then it will make an impulse output through its axon to other cells. And that's not showing up. Right there. And so this is, if you know anything about neurobiology, this is a very simplified model, but what this might look like for a classifier is you have some input, which will be your feature vector, and then you weight each of these features and then sum together, and if that sum is greater than a threshold, then it will produce a +1. Otherwise, it will produce a -1. And people also get very excited about neurons and say, what if we made networks of these classifiers? And that's sort of some of the inspiration for neural networks, which we'll see in a couple of lectures. But today, we're just going to talk about the one case where we have a single neuron model, which is called a perceptron. It's like a synthetic neuron, and how we can, what we can do with these single perceptrons. So as we saw, the input is going to be each of the feature values from your example, and then each feature for this classifier has a weight. And then you sum over all of these weighted features and compare it to a threshold, and that's called the activation. And if the activation is greater than the threshold, then you output +1, otherwise you output -1. So you have some activation, and then for each of, here's your feature vector x, which is a function of your example x, and then you weight each of these, and you create a weighted sum, and this weighted sum is your activation. And of course, this is just a dot product. Create a weight vector w of all of the weights and take the dot product between this vector and your feature vector, then that's what your activation is. And if your activation is greater than a threshold, then you output +1, or you output -1 if it's not. And if you, generally you just compare it to 0, and if you want to have a non-zero threshold, what you can do is make a feature vector where the first feature is always 1, and this is called your bias feature, and then the weight corresponding to that bias feature will be the threshold that you're comparing against. And then once you take your feature vector and dot product with your weight vector, then you simply compute the weighted sum and then compare it to 0 to produce your output. Yes, question?
Why don't you just compare it to like a number greater than 0?
You could do that. It would do the same exact thing. For simplicity, it's nice to have this dot product form right here without having an additional term over here. And we'll see actually on the next slide why it's nice to just compare to 0 versus comparing to a positive number. Yes, question?
Geometrically, is this just like kind of on a hyperplane that separates points?
Yeah, so your weight vector, you'll see there's a decision boundary that's determined by that weight vector, and that's it's like a separating hyperplane between your points. And we'll see in a couple slides what that hyperplane looks like. So you have a weight vector, so if you have all of your features and there's a weight for each feature, then this weight vector is in the space of your features. So if you have 10 features, then this is a 10-dimensional space. And then your feature vectors are going to be in the same exact space as this. They'll have one value for each feature. So if you have your weight vector right here, and then a feature vector for your point x1 right here, then the dot product will determine the classification that you make. And if the dot product between W and F is greater than 0, then you output +1. So geometrically, what this means is, since the dot product is positive, if this actually is representative of what the angle between these two vectors are. And if the angle is less than 90 degrees, then the dot product is positive. And therefore, we can just simply look at the angle or just have this be positive, and if they're pointing in the same direction, then that's a positive example, versus if you have a feature vector that's pointing in the opposite direction and the angle between the weight vector and the feature vector is greater than 90 degrees, then the resulting classification is going to be negative, and it's going to be -1. So this one would be classified as +1, and this example would be classified as -1. And so what this defines is that if this is your weight vector and you have some plane right here, basically all the vectors that are pointing in the same direction as the weight vector are going to be positively classified. So all the points that are on this side of the hyperplane are going to be positive, and all the points that are pointing away from the weight vector are going to be negative.